Hi, welcome to Core Concept 6. And I was going to do some problems after Core Concept 5, but as I started doing them, it just occurred to me you'd have to understand the concept of equilibrium and how a free body diagram representation can be looked at before you start really doing those problems. So I want to use this as a stepping stone before we get to doing problems. I also added a small section in the basics playlist on equilibrium and free body diagrams, but if you haven't watched that, that's okay. I will go through this section and I'll be fairly thorough with what you need, right? And I'm going to start off. Um, this time, I'm going to start off with my example that has come up several times, and we came across that in friction. And I'm going to use that example. Now, when we did those problems, we often wrote, or drew this inclined plane. We put our object there, and obviously, we started playing with forces here. So we had our little mass times acceleration. We had our little cosine of theta, our sine of theta component that came in. We had all these things. We had a frictional force that we applied here, right? That we had all of that, right? And I think you're familiar with it. But let's take that a step forward and see what it actually means, right? So I'm going to use this example, and first let me take that out, right? I want you to start visualizing things in a free, as free body. So my favorite box of coffee capsule. So we'll start this off and we'll work on this as if it's a mathematical problem. And let's try and understand this a little bit. So this is 128 grams. This is the weight, the net weight of the coffee. So we're going to assume that we'll assume that the cardboard packaging is no weight. So here I am. We know there is some friction. You see, it doesn't necessarily move easily. We also know that if we turned this way, it didn't slip, didn't slip, didn't slip. And then finally we got to a point where it slipped, and we studied all of that in friction. But let's now say I'm at this point, and hypothetically, I'm going to say I'm at 30 degrees, at an incline of 30 degrees. I have this box, mass 128 grams, and I'm going to ask you a question. What is the force of friction holding the box in place? Right? That's the question, right? It did slip. Just when I said holding it in place, but at 30 degrees, doesn't slip. This is work with me on the fact that this is 30 degrees, right? What is the force of friction that is holding this box? Based on that, I will work with you to look at it as a free body. So I'm not going to draw my slope here, but instead, all I do, okay, I'll use the skull for my box. So there's my box. And this is how I'd like you to start looking at things. Because if you have an exam question that asks you for a free body diagram, this is probably what it's going to be. So there's my box. Now let's just take a look at what's going on with this box. It's got a mass, right? And I'm going to use this color. M is equal to 128 grams. And because we want to use standard units, it's 0.128 kilograms, okay? We know that. Now, I did briefly address a center of mass. So what I'm going to do is I'm just going to plot this here. And you could do this from any point, preferably, you know, here or in the center, but I'm going to use the center just to illustrate what's going on. And when we talked about vectors, at the end of the day, it doesn't matter where you draw it from. So I'm going to first say, well, we know for sure that is mass times acceleration due to gravity. We know that exists, right? Which means we also know that we can resolve this along the line of the slope. Now, the slope was 30 degrees. So if this is 30, right angle, which means this is, let me just In a free body, you wouldn't do the dotted line. I'm only doing this as an illustration. If this was a 30-degree plane, then that would be 60 degrees, right? So you've got that part. What would that force be? That resolved force would be mg cosine theta. So this would be cosine of 60 degrees. I do like 60 degrees, cosine of 60 degrees, very easy to work with. And we also know that there is a reactive force. And again, when we studied vectors, I'm gonna draw that here, acts along the plane, and that's the frictional force. What is the frictional force holding this box in place? Obviously, we have two other components that I'm going to talk about. So one is the box and the weight, that's this component here, right? And I would just, obviously it's sine of 60 or sine of 30, there is a component here. And likewise, there's the reactive force that's pushing the box up from the floor. Maybe use this as another. So that's the reactive force pushing the box up. And those two cancel, the box isn't moving. It's a fixed plane, right? It's a fixed base. In this case, your reactive force here should be equal to mg cosine of 60 for it to cancel out. So you would say force of friction is equal to, and I'm just going to switch to and if you put in all the values here, it's 1.028 times 9.8. This is kilograms, this is meters per second. Cosine of 60 is just 0.5, and that would be kilogram meters per second square, or for force in newtons, right? Just letting you know that this is also kilogram meters per second square, right? And then you can do the math, and what would that math be? So this would be about 0.064 times 9.8. That would be times 10. So that would be approximately that many newtons, if my math is right, right? So half of 0.128 is 0.06, actually 0.6 newtons. Look at that. It's approximately 0.6 newtons. And that would be the reactive force. And that's how you calculate it, representing a free body diagram. The box is in equilibrium, meaning all of its forces cancel out in all the directions. Obviously, if this angle was higher and the box was slipping, force of friction, we've surpassed force of friction, we've exceeded the force of friction, there is no force and it's moving, the box wouldn't be in equilibrium. So this is a classic case that I would kind of like you to remember and use when you work on problems. I'm going to get another case. This one's a little more interesting. And this time, I'm going to use my bunch of keys. So what I've done here, now this is a string and it's not elastic, meaning it doesn't stretch, it's wool, right? And here's a rather heavy, I'd say this is about, call it 200 grams of all metal, right? And I've tied it up here. I wanted to make it an equilateral triangle so it's a little easier for you to digest. And if this is horizontal, what I've done here is I'm hanging these keys here. Clearly, they won't move. I mean, it's not going to fall. And, I could do all of these. I mean, I could move it here and all that, but for this example, I'm just going to work with this. So if this was my case, how would I represent the forces on this? And let's work with this and see what we got. So this is about 30 centimeters, and this is about a little over 30, but for the purpose of this example, we'll just assume it's all 30, right? And then we'll also make this simple by saying we'll call this end A, we'll call this end B, and we'll call this as C, right? So I'll put this away and then start working on drawing this out. So it looks fairly straight. So let's just say I can never get that. Okay, so that's a string, and that, let's say, is the object that I have. We'll write C on this side. Maybe give this another color. So what's going on here? If this is staying in equilibrium, we know there is mass times, we know that. Easy. But now we have two forces, and how do we represent this in a free body diagram? So let's just say equilateral triangle. So we know that we did state that this was 30 centimeters, and we know that each of these is about 30 centimeters, and this is 30. So in an equilateral triangle, the angle here will be, your math, just 60 degrees. Whether these are 30, 30, and 30, 40, 40, and 40, didn't matter, right? That's 60 degrees. So we understand this, and now let's take this and try to make a free body diagram of those keys. So I'm going to just draw the key punch here, represented this way, right? Force 1, right? And then I have two forces. If you think about it, it was as if the string was pulling the keys, right? Its weight is pulling it down, or rather bringing it down, and the two strings were holding it together. So there's two forces here. You would not in any, and if this bunch of keys didn't move, the net effect of all these forces would be zero. And if you had to do this and say, what is the force? Now, again, the strings were the same material, the angle, the length, all of those parameters are the same. It is safe to assume that force on string 1, or actually the better way to do it is force on string AC and force on string BC. You could say force on string AC is equal to force on BC. And what are they? So if you had to calculate it, what would you do? Very simple, right? You could do a technique of resolving these forces. You can bring them onto the same line as the vertical force, that's the weight of this object. And if I did that, I would effectively have a force here, right? And I could say force reactive, if this is mg, right? And you would say the reactive force is also equal to mass times acceleration due to gravity. So what would force reactive be? Well, if that was 60 degrees, we know that this is 30 degrees, and this is 30 degrees as well. Again, I used an equilateral triangle. you could do this by moving the positions and you'll see how values change. So in this particular case, what is you can resolve this force, whatever this be, this is the unknown force, onto this line, and that would be force BC cosine of 30, right? And this would come back here. We know from our study of vectors, vector addition, effectively FR would be with the direction maintained would be force vector AB cosine of 30 degrees. Why 30? Because it's resolving into 30 degrees. Add that to force vector BC. Maybe it's not AB, it's AC. And cosine of 30 degrees. That's this 30 degrees. You can do the math. We know these two are equal. You can substitute for either one, get M and G there, which is, let's say, 200 grams and 9.8 meters per second squared would be approximately 19.6. Actually, it'd be 1.96 because it's 200 grams is 0.2 kilograms. So you can do the math there. And if I just did this, or you can do it yourself, I think you know the answers. This is fairly straightforward math. So you bring this, substitute in to, let's say, FAC, cosine 30 is an easy one that you would know. MG, so that's about 1.96. And you can solve for FAC, and FAC is equal to FBC. So you can get these two forces pretty easily solved. So that's the idea, free body and the equilibrium of forces, and sort of how the math comes together, right? Pretty basic stuff. When it comes to the high school level, they'll probably just throw you problems like this and have you resolve it. But the main point I want you to take away here is make sure that the angles that you pick are correct, right? That will determine the answer. And I'll highlight that again with another example, just an extension of what I have here. But this time I'm just going to play with it a little bit and have you think through what's going to happen, right? So let's just play with this a little bit. Go back to the string here. Okay, so that's what I had, right? And if it was centered with something like this, that's the equilateral triangle. But because this is not entirely smooth, I could just, it's going to move back to the center. Why is that happening? If I brought this here, now this is something you can think about. What is going on? Why is it that when I did this, for example, I did this, it came back here. It wants to find equilibrium. Actually, yeah. And it sort of comes back to this equal length. And obviously, it won't be 100% equal because I've got my finger here, so there's a little bit of tension coming in from my finger, but generally it wants to be there. If I moved it all the way here, it wants to come back, right? It cannot find balance when this happens. And notice what happens on cosine 30. So here we had two cosine 30s. There's a cosine 30 on either side holding it. But when I come up here, if this is 90 degrees now, this is in one line, that force is not entirely getting resolved here. There is this component and it's a slight pull from here that's now bringing it down, right? So that's an important idea that you can work on. But let's do this. Let's keep it somewhere here and see what, fairly balanced. But the tension on these two, this is very loose. If you can notice, this is much looser. This one's a lot tighter. The string is a lot tighter. So if I let go and see if I can, let me try and play with this a little bit. Look at that. It can still, wow, this is a lot more tighter and this is a lot looser. This is a lot looser. This is very tight. Why is that happening? Clearly, the reactive force of this, when resolved here, is much stronger. So there is a lot more force acting on this. There's a force of tension on this string. If this force of tension exceeds the tensile strength, something that some branches of physics and a lot of people in chemistry and metallurgy would study, if that force exceeds, the tension force exceeds the tensile strength of the string would snap, right? And obviously here, there's not as much tensile strength, so there's, I can still move the string around. It's pretty relaxed. But as I brought it close, the cosine 30 component, if you thought about it, this angle here reduces, which means as the angle approaches zero, the cosine value increases. More and more of the reactive force holding this is felt here and much less here, right? So that's the fundamental idea that you need to carry with you. I'm going to leave you with an interesting problem that you can attempt yourself. So supposing I have this key here, and I'm going to hold it there, right? So this leaves if I brought it all the way and tugged on it, it's, both of these feel some tension, but I'm going to hold it here in such a way that the angle that comes up here is 90 degrees, exactly 90 degrees, right? This string is very loose and that's a bit more tight. I'm applying force parallel to the wooden stick. I'll leave you with the idea. Calculate what force I am applying with my right hand on the key bunch to keep that key in that position. And if you figured it out, that's it. Pause the video, go home, be happy. If not, let me attempt to solve it. Now, the strings haven't changed. There are a total of 30 and 30, so 60 centimeters. So what I'm going to do here is I'll play with this a little bit. If my A and B were 30 centimeters, okay, and this hasn't changed, but now I have that representation of a right angle triangle, and that's, say, if that's C, right? I know that AC plus BC, as was the case, is 60 centimeters. And I know AB is 30 centimeters, right? I can now calculate what this angle is. How would you do it? Work the math out, right? If you know your Pythagoras theorem and a little bit of trigonometry, you can solve for this. Once you know this angle, then you come to the free body of the keys. You know that it is in equilibrium. I did explain that I was trying to pull this back this way. Okay, and it was in equilibrium. The resolving force components of the string would be here and there, and this would be theta. And you'd be able to identify what's going on. And in order to keep it entirely balanced, you could estimate what this force would be. Now, you will find out that there is this component of reactive force that could be resolved here. There would be it's not going to be entirely zero. There is a component here, but you will typically resolve this reactive force against this direction, and you'll realize you can calculate what this value would be, right? So this is just an idea, and hopefully you can solve this yourself. Okay, so that's the idea of equilibrium and free body diagram and how you would resolve forces and work the math. I think we're now ready to do some problems because it should hopefully give you a better view of how to visualize these and how to put them on a paper and start putting solutions together. All right, we'll see you in the next video.